This time we're going to try to relate solubility in water to predicting whether a compound formed is a precipitate or not during a reaction. So let's take a look first at what solubility in water means. That means it's dissolvable in water. Let's take, I drew out some ions here, like say a small crystal of table salt, NaCl. It's held together by ionic bonds here, and I'm not going to draw out each one, but just give you a feeling for it. And they're pretty strong. But in the presence of water, let's draw the water molecule here. So we have H2O, so that'd be an oxygen and two H's. Little Mickey Mouse head there. And a water molecule is bent like this, kind of V-shaped, and the oxygen side tends to be more negatively charged, and the ears, the hydrogen side, tends to be more positively charged. So the water molecule will rotate around and orient itself so that the negatively charged oxygen side is nearest the positive sodium ions. So we end up with water molecules lining up like this. The negative side there, the positive side of the water molecule. Get a whole bunch of them there, lining up like that, and they're going to exert quite a pull, quite an attraction on that sodium ion. It should be stronger than the pulling force of the chlorides on the sodium. And so what happens then is the sodium gets pulled away. Just erase it here. And we have one less ion hooked in that crystal lattice structure. The sodium's pulled away, let's say it's over here now, and it's surrounded by water molecules with the face side of the Mickey Mouse head, if you want to call it that, facing in toward the sodium ion, with the oxygen side being negatively charged and attracted to that sodium. So those water molecules effectively prevent the sodium from hooking back up to its crystal lattice. How about with the chloride ions? The chloride ions are negatively charged. Water molecule has the ability to take care of those too. Just that it will rotate around so that the ears of the water molecule, the positive end, would be oriented nearest the negative chloride ion, and the negative end of the water molecule would be oriented farther away. You get enough of those nearby, they're going to exert a pulling force on that chloride so that it gets pulled away from the crystal lattice structure. And now we have one less chloride ion in that crystal. The chloride ion then would be, let's say, maybe over here, surrounded by a whole bunch of water molecules with the ears, if you want to call them that, facing the chloride, because the ears are positively charged, and remember, positive charges are attracted to negative. The waters then surrounding that chloride ion prevent it from hooking back up, and so forth. So the chlorides, so sodium chloride, which is what this crystal is here, is soluble in water because of this process. Now there's a set of solubility rules, and we can take a look at them up here. Solubility of common compounds in water, and this is only for water now. We're not talking about other solvents. It's not totally complete either, because I was just looking at this one. It says sodium, potassium, and ammonium ions, but I can think of other ions like lithium, another alkali metal such as sodium and potassium, which also follows this rule. So we could add lithium on here if we wanted to also. And there are probably some other ones too. Okay, well, let's take a look. Above this horizontal line, we have compounds that are soluble in water. They contain ions that are soluble in water. And then below this horizontal line, these are common compounds that contain ions which are insoluble in water. Insoluble meaning not soluble. Not soluble. And if they're not soluble, then they settle out of solution as a precipitate. So in other words, they form a precipitate. And a precipitate isn't like rain. In chemistry, it's basically a solid that settles out of solution during a reaction because it's insoluble. Okay, well, now it's time to practice a few. Which of the following compounds are soluble in water? Let's take a look at the first one and use our solubility rules. Oh, before we do that, there are exceptions. Please make sure we look at the exceptions. Like, for example, acetates are soluble in water, any kind of compound containing acetate, except if there's silver in it. That makes it only moderately soluble. So that means that some of it precipitates out. Chlorides are soluble usually in water, except if you have silver chloride, mercury 1 chloride, or the lead chlorides. Those would be insoluble. So the exceptions are not soluble. Sulfates are usually soluble in water unless you have barium sulfate or lead sulfate. Calcium sulfate, mercury 1 sulfate, silver sulfates are slightly soluble, but that also means that a slight amount will be insoluble too and precipitate out. Let's look at the common compounds that would be insoluble or not soluble in water that would tend to precipitate. Compounds containing silver ions are insoluble. Exceptions would be if there's silver nitrate or silver perchlorate. Sulfides are usually insoluble, but there are exceptions, right? If it's sodium sulfide or potassium sulfide, ammonium sulfide, magnesium, barium, calcium. So there are exceptions. So these are the insoluble ones, but there are exceptions. And if there's exception, that means that it's soluble. All right, well, let's try it out, and we'll just kind of look through the solubility rules for each one of these. How about AgNO3, which is silver nitrate, right? We know that's a nitrate ion. That means silver nitrate. Oh, look here. In the soluble section, it says all nitrates are soluble. So, definitely soluble. So what does soluble mean again? It's dissolved in water, not a precipitate. How about 2, KCl? Well, potassium chloride. I look up here. In the soluble section, it says chlorides are part of the soluble section, right? Chlorides are soluble. Is potassium an exception to the rule? Nope. So that means KCl is soluble. How about BaSO4? BaSO4 is barium sulfate. So let's look at the sulfates. That's a sulfate, right? Sulfates are soluble except barium and lead sulfate, and then we have some other ones that are slightly soluble. So is barium sulfate soluble? No, it's not soluble. In other words, it is a precipitate. If you have a reaction and barium sulfate is one of the products formed, then that will be a precipitate. It'll settle out as a solid. It's not soluble. How about AgCl? Let's take a look. Ag stands for silver, Cl is chloride. We'll go up here and look at the chlorides. Chlorides are soluble except silver. Okay, so that's not soluble. It is a precipitate. I'll just put PPT for precipitate. How about lead sulfate? Lead sulfate. The sulfates are soluble except barium and lead and some others. So lead is not soluble. It is a precipitate. Let's go over to this one now. CaC2H3022. What is this? Well, if we look at our polyatomic ion sheet, C2H3O2, that's an acetate ion with a negative, has a -1 charge. So calcium acetate. We'll look up acetates. Do we see them around here? Acetates, right here in the first section, the soluble section. Acetates are soluble, aren't they? Exceptions would be silver acetate, which is only moderately soluble, but this is calcium, so that's not one of the exceptions. So it is soluble in water. How about another one? BAS, barium, and then S stands for sulfide. We'll look at the sulfides here. Sulfides are in the insoluble section. Sulfides are not soluble. Let's look at the exceptions. Sodium, potassium, ammonium, magnesium, barium. Barium is an exception. So since this sulfide is in the insoluble section and barium is an exception to that, that means that barium sulfide is soluble in water. Soluble, because it's an exception. How about Fe2S3? Well, that's another sulfide. So we'll go to the sulfide section, not sulfate. Sulfide. Is iron an exception? No. Iron's not one of the exceptions. So since sulfides are in the insoluble section, iron sulfide is insoluble, or in other words, not soluble, right? So it forms a precipitate. How about calcium carbonate? Well, the carbonates are right here. Carbonates are normally insoluble, aren't they? Is calcium an exception? Potassium, ammonium? No. So that means calcium carbonate is also insoluble or not soluble in water. It forms a precipitate when it's produced during a reaction. How about the last one? NH4, if we look on our polyatomic ion sheet, is the ammonium ion with a +1 charge. So this is ammonium carbonate. If we look up ammonium, it's always soluble, isn't it? Always soluble. We look up carbonates. Carbonates are insoluble except, ammonium. How about that? So we find then that ammonium carbonate is soluble. In other words, it does not form a precipitate. It's soluble in water. Okay, so there are some examples to help give you a feel for this kind of thing. Now let's see how we can apply the idea of solubility in water if we have solutions containing different chemicals and we're trying to predict if a reaction occurs or not. One driving force which will allow us to predict a reaction occurring is if there's a precipitate forming, and that has to do with being insoluble in water, right? Not soluble. So let's take a look at this first one. Are we going to end up with a precipitate over on this side? If we will, then the reaction will occur. If not, well, probably not, unless there's some other motivator for that reaction to happen, like maybe a gas forming or electron transfer or something like that. Well, barium sulfide. Remember what we found for barium sulfide before? It was soluble in water, wasn't it? Sulfides are normally insoluble, but barium is an exception to the rule. So that means that this is dissolved in water. It's aqueous, right? It's aqueous. So, how about calcium chloride? Calcium chloride, normally soluble in water. Is calcium an exception? No. So it's also aqueous or soluble in water. So these two can mix easily together because they're totally dissolved in water. AQ stands for dissolved in water. If we look, we can see that we can guess that it's a double replacement reaction with barium going over and hooking onto the chloride and calcium going over and hooking on to the sulfide. So we'd end up with CaS and BaCl. And since Ba has a +2 charge, chlorine is a halogen with a -1 charge, we need 2 chlorides for every 1 barium, so I need to put a little subscript 2 there. Now that means that we have a neutral compound. How about calcium sulfide? Calcium is an alkaline earth metal with a +2 charge. The sulfide ion usually a -2, so that adds up to 0 just fine. Are either of these a precipitate, or are they soluble in water? If they're soluble in water and no precipitate forms, this reaction won't occur. Let's see, calcium sulfide. Sulfides are insoluble in water. Exception would be calcium. So that means that it is soluble in water and it stays aqueous. No precipitate there. How about barium chloride? Chlorides are normally soluble, aren't they? Chlorides are in the soluble section. Is barium an exception? Silver, lead. No, it's not. So we find then that this is also soluble in water. No precipitate is formed over here. Therefore, guess what? If there's no precipitate forming, then this reaction is not going to occur. No reaction happens. Okay? So that was kind of a royal waste of time, but in terms of being able to end up with products. But we did see, we were able to use the solubility rules and determine that no precipitate will form. No precipitate forms. Therefore, no reaction happens. Let's go to the next one. AgNO3. We'll look real quick. This is a nitrate, isn't it? All nitrates are soluble. So that means that this is dissolved in water, and I can put AQ there to indicate dissolved in water. How about this one? Iron 3 acetate. Well, it says here that all acetates are soluble in water too, and iron is not one of the exceptions. Only silver is. So I'll put AQ here, which says that this compound is also dissolvable in water. How about the products? Well, we see a 2-part compound reacting with another 2-part compound. It's probably going to be, you guessed it, double replacement, huh? So let's do that in our head, and then bring over the Fe and hook it onto the NO3. And then we'll have the Ag, which is the metal, goes first, and the non-metal second, which would be the acetate. Now we'll try to make sure that our compounds are written correctly. NO3 is a nitrate with a -1 charge. The iron over here had a +3 charge. So that means I need 3 more nitrates so that a -3 adds to the +3 and equals 0. So I'll put parentheses around the NO3 and put a little subscript 3 to the right of it, meaning we have 3 NO3s for every 1 iron ion. Silver has a +1 charge. The acetate ion, if you look at it on the polyatomic sheet, has a -1 charge. That adds up to 0 already, so it's just 1 of these for every 1 of the acetates. But now, are any of these precipitates? If not, then there's no reaction. How about this one? Well, this is a nitrate, isn't it? Nitrate. All nitrates are soluble. So that means that we put AQ next to that one. How about silver acetate? It says acetates are soluble except silver, which is only moderately soluble, which means that some of this actually is insoluble and it acts as it's a precipitate. So yes, this one does happen. A reaction does occur here. This is the product right here, the silver acetate. And so what would happen? If you put all these two reactants into a test tube in water, they would react together. So there's the test tube right here. They would react together and you'd get some of this silver acetate precipitating out and forming a clump at the bottom. It would form a solid at the bottom of that aqueous solution. That would be the silver acetate precipitate there. Okay? Next one. Here we have sodium carbonate or washing soda reacting with magnesium sulfate. Well, let's check them out and make sure that they're soluble in water to begin with. Sodium carbonate. Carbonates are normally insoluble except sodium, potassium, ammonium. So this is soluble then, because sodium is an exception. So I put AQ there. That's good. How about MgSO4? This is a sulfate. Sulfates are normally soluble. They're in the soluble section, except for barium and lead, calcium, mercury, silver. Magnesium is not one of those exceptions. So it too is soluble, so I'll put AQ there for aqueous. Two-part compounds reacting together, we get a double replacement reaction. So that means we have Mg as the metal that goes first, hooking on to CO3, the non-metal. And we have the sodium, which is the metal that goes first, hooking on to the SO4, the sulfate, which is the non-metal. The next step is to take and check the compound to make sure it's written correctly and the charges add up to 0. Magnesium is an alkaline earth metal, +2 charge. Carbonate is a -2 polyatomic ion. So that adds up to 0, so that's good the way it is. Sodium sulfate, not so good. That's an alkali metal with a +1 charge. The sulfate has a +2 charge. I'm sorry, a -2 charge, +2. I'm dreaming. Okay, so a -2 charge for this sulfate. So I have to fix that by putting a little 2 subscript immediately to the right of the sodium. That doubles the number of sodium ions. Now we have a +2 and a -2 adding to 0. Now we need to check to make sure if there's a precipitate or not. Magnesium carbonate, what do you think? Okay, well, carbonates are not soluble. They're in the insoluble section, and magnesium is not an exception. So that means that it is a precipitate right here. So magnesium carbonate is insoluble, and that means that magnesium carbonate is a precipitate. It'll sink to the bottom of the test tube, let me say, as a solid. How about sodium sulfate? Well, it says all sodium ion compounds are soluble in water, and sulfates are also soluble, so we get double confirmation there that this is going to be soluble. And I'll just put AQ for aqueous there. So if we have our test tube again with our 2 soluble reactants or aqueous reactants in there, and they react together, which one of these will be the precipitate? The MgCO3, and that will settle to the bottom as a solid. See it? The solid is forming. Okay, that would be the magnesium carbonate. Last one and we'll be done. Here we have KOH reacting with ammonium phosphate. Well, it says K is potassium. All potassium compounds are soluble, so I can just go with that. There's no exception. If we want to double check, we can look at the hydroxide section, OH, and it says hydroxides are insoluble except for sodium, potassium, ammonium, barium. Okay, so from both ends we find that it's going to be soluble in water or aqueous. How about ammonium phosphate? Look up here in the soluble section. Ammonium is one of those that's always soluble. Phosphates usually mean insoluble, but we have the exceptions, one of them being ammonium. So both of these then are going to be soluble in water, and so when you put them in the test tube, that you won't even see any solids at all. They'll just be floating around until they react. And we see this is a two-part compound. We have a metal and a non-metal reacting with another. Well, this isn't a metal, but it's a positively charged ion and a negatively charged polyatomic ion. So this would be like a metal in terms of its ability to give away electrons. So we'd see that the potassium might go over here and hook onto the PO4. The ammonium would go over here and hook onto the OH. So we'd end up with NH4, which is the ammonium OH, plus K hooked onto the PO4. Let's check to make sure the compounds are written correctly. NH4 is an ammonium, has a +1 charge. OH is a polyatomic ion with a -1 charge. That adds up to 0. But ammonium compounds are always soluble, no precipitate there. How about potassium phosphate? Potassium is an alkali metal with a +1 charge, so I'll put that there. The phosphate is a polyatomic ion with a -3 charge. Therefore, we need 3 of these potassiums, so I'll put a little 3 subscript to the right of the K. Is it soluble or not? Well, it's potassium in there, so remember, if it has potassium, it's always soluble in water. So, in this last example, we're just going to end up having that test tube there with nothing sinking to the bottom. No reaction occurred, basically. No reaction happened. No reaction. Why? Because no precipitate formed. And forming precipitate is one way to drive a reaction forward, have the reaction occur. Like I said, other ways would be if there's gas formation or if there are electrons transferred, something like that. Okay? So that's it, guys. Thank you.